Hello everyone and welcome to the next webinar from Würth Elektronik eiSos. My name is Silas Zorn and I will moderate this webinar today. Our topic of today's webinar is voltage dependence of ferroelectric class 2 multilayer ceramic capacitors. Our speaker today is René Kalbitz. René, hi, cool to have you here. Before we start with the webinar, I would like to give you some more informations. You will be muted during this webinars. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions into the chat function. So after the presentation, it will be about 45 minutes long. René will answer them live in a short Q&A session, and if we are unable to answer all the questions live after the presentations, so we will answer it later on via email. So now last information from my side. You will all receive the link to the recording as well as to the recording and the presentation. You will all receive that after the webinar today. So now I will hand over to René and I wish you an exciting webinar.
Today I would like to talk about the model development of ferroelectric class 2 MLCCs and provide a background on ferroelectricity. My name is René Kalbitz. I'm working as product manager at the capacitor division at Würth Elektronik. I'm mainly concerned with supercapacitors, but I'm also working on other application-oriented development, such as polarization models for MLCCs, our today's topic. Multilayer ceramic capacitors, short MLCCs, are the most common capacitor type. At Würth Elektronik, we have about 1,000 part numbers in our portfolio. They are available in different classes that are distinguished by the used dielectric material, capacitance volume ratio, and thermal stability. Most prominent is the class 2, which has typically a high volumetric capacitance and is used for buffer and coupling applications. Class 2 MLCCs or ceramic capacitors have high capacitance, but the capacitance decreases with increasing applied DC voltage, as is shown here in the capacitance and the impedance plot of a 10 microfarad MLCC over a range of 40 volts. As you can see, the capacitance spectrum is shifted to lower capacitance values and the impedance spectrum is shifted towards higher frequencies. In other words, the characteristic frequency indicated by the minimum in the impedance spectrum and the asymptotic peak in the capacitance spectrum is shifted to higher frequencies. There is nothing one could do against it. All class 2 capacitors show this behavior independent of the manufacturer. You may find some variations, but the overall behavior is the same for all class 2 MLCCs. It is a physical behavior characteristic for ferroelectric materials. Ferroelectricity is actually the reason why they have such a high permittivity, and that is to say volumetric capacitance. However, the developer has to, of course, to anticipate this behavior to find the suitable capacitor. Keyword oversizing. So you might ask, how am I to know the capacitance value for a certain voltage, or are there other effects, and why do they show this behavior anyway? Which brings me to the outline of the today's talk. In this talk, I will first briefly revise the background of MLCCs and the prominently used ferroelectric material barium titanate. I will show you the effect of the long and the short-term polarization, discuss how the polarization affects capacitance measurements and what the so-called memory effect is. Give the introduction to the mathematical model that describes the voltage as well as the frequency behavior of MLCCs, and illustrate how it is implemented in Würth Elektronik LTspice models, which are freely available. In principle, the MLCC consists of interdigitating electrodes of alternating polarity, which, as in this example here, can form a parallel connection of capacitors, leading to an increased effective electrode area. Other geometries may also be possible, but it is always some sort of multilayer electrode structure, hence the name multilayer ceramic capacitor. The actual ceramic is not a monolithic material block, but is formed from sintered ceramic powder, which consists of small sub-micrometer sized grains. As illustrated in the scanning microscope picture here on the right, parts of the SEM have been post-processed to highlight the electrodes and the grainy structure of the material. The grain itself then forms so-called polarization domains, which give rise to the ferroelectric behavior. The term ferroelectricity is used in analogy to ferromagnetism, in which a material exhibits a permanent magnetic moment. It describes the property of a material to form electric dipoles without applying an electric field. Ferroelectricity only occurs in crystals that have a unit cell with no center of symmetry, that is to say, non-centrosymmetric shape. A prominent ferroelectric material widely used in class 2 MLCCs is barium titanate. The figure on the left shows the barium titanate unit cell, in which the positively charged barium ion is shifted slightly in this representation upwards with respect to the center. Thus, the unit cell is slightly more positively charged on the top side and somewhat more negatively charged on the bottom side. Since the permanent electric dipole interacts with applied fields, the polarizability, hence the permittivity of such material, is voltage dependent. In a ferroelectric material, all direct and indirect neighboring cells form the aforementioned dipole, which points in the same direction. The alignment of neighboring dipoles results from total energy reduction due to dipole-dipole interaction. The ferroelectric attempts to attain a domain configuration that minimizes the total energy while satisfying both electrostatic and mechanical boundary conditions. In an idealized system, all the dipoles in the crystalline material would collectively point in one direction. All materials, however, have minor imperfections that cause the collective orientations of dipoles to be limited to areas called domains. So each domain may have its own polarization direction. The size of the domains, the crystal configuration at domain boundaries, the orientation of the dipoles within the domains influence the polarizability and thus the permittivity of the material. Therefore, the capacitance of MLCCs will depend on all those things as well, not only on the voltage. Let's interpret the capacitance voltage measurement on of an ferroelectric capacitor on the example of a 10 microfarad MLCC, class 2 MLCC, of course. The polarization behavior of ferroelectric materials depends on the actual state of polarization. I'm missing my, no, here we have the cursor. The polarization is essentially, once again, the polarization behavior of ferroelectric materials depends on the actual state of polarization, as shall be discussed with the capacitance voltage plot in the middle here and the polarization voltage graph given on the right. The polarization is essentially the amount of accumulated charge at the capacitor. On the left, you see how the DC voltage was swept in this measurement. During the measurement, a sinus probing waveform of a certain frequency is applied to measure the capacitance of the capacitor. The AC probing waveform has a fixed amplitude throughout the entire measurement and induces a small periodic change of voltage, delta V or dV. On the sinus signal, the DC voltage is superimposed then, allowing the reorientation of the domain polarization. Okay, let's consider branch 1. That's the dotted green line. We start with randomly oriented domains here. With randomly oriented domain polarization, the capacitor is subjected to the test signal. With the increase of DC voltage, the dipoles eventually become aligned, leading to increased polarization. As is illustrated in the insets here, I desperately try to use the cursor, but from time to time it just vanishes. I hope you can see it. Saturation polarization is reached when all dipoles ideally point in the direction of the external field. As the voltage increases, the dipoles become aligned and the dipole movement becomes more and more restricted, which leads to a reduced charge change delta Q or dQ. Hence, the capacitance, which is per definition delta Q over dQ over dV or delta Q divided by delta V, decreases with increasing voltage. That's what you see here in the middle. When the applied external field E, which is proportional to the applied voltage, has aligned the majority of domains, the dipoles remain in this position, even without the external field. The collective alignment creates an internal stabilizing coercive field. The material retains this state, so to speak, and remembers the polarization. Yeah, hence the term memory effect, which is sometimes also used. Ideally, the polarization at maximum voltage is referred to as saturation polarization or spontaneous polarization. Yeah, all right, let's consider branch 2, that is the blue graph. As the voltage of the external field is reversed from positive to negative, the dipoles relax slightly but remain in their overall polarization direction due to the internal coercive field EC. The polarization state at 0 volt is referred to as remanent polarization or PR. Any reversed external electric field will have to exceed the coercive field to reorient all domains into the opposite direction. At the position of EC, the strain on the dipoles is least. Thus, the material's permittivity is largest, and the capacitance shows a local maximum. With the increase of the polarization into the opposite direction, then the capacitance decreases to the same values as for positive values. Which brings me to branch 3. If the voltage then is driven from negative to positive, the dipoles reorientate again when the externally applied field exceeds the coercive field. This again leads to a peak at the capacitance, where this time at positive voltages. The process is similar to the one described before. Branch 3, similar practically to branch 2, well, except it is shifted along the x-axis towards positive voltages. So that behavior, which I just described, is in principle the same for all class 2 MLCCs. However, depending on the material composition, the ferroelectric behavior may vary. Oops. Something strange just happened. Anyways, different ferroelectric behavior actually means differences in the capacitance decrease as a function of the applied DC bias. What you see here are measurements on 10 microfarad MLCCs from different producers. We conducted a market survey to analyze possible differences in product performance and try to pinpoint reasons for it. So we did kind of a reverse engineering. As you can see, all show a decreasing capacitance as the voltage is increasing, as is typical for class 2 MLCCs. This capacitive DC drift is, however, not the same for all MLCCs, although they have roughly the same datasheet parameters such as form factor, capacitance, rated voltage, and material specifications. The MLCC from Würth Elektronik, in this case here in the purple graph, is in a group of producers that show a less pronounced decline compared to MLCCs from producers 3, 4, and 5. In the mid-voltage region, one can find differences of about 30%. Obviously, it is important to know the degree of decline, which is why we give actual measured graphs in the Red Expert. We have performed not only impedance measurements, but also an analysis of the actual used ceramic material. That analysis was performed in cooperation with the Technical University of Berlin. The samples were firstly encased in epoxy, then cut, grinded, and etched before they were subjected to a scanning and energy dispersive X-ray spectroscopy. Based on that, we were able to analyze particle size distribution, electrode spacings, as well as the chemical compositions. The picture and graphs shown here are just examples to give you a rough impression of what was going on during that analysis, or what we actually did. We were especially interested in the analysis of additives like yttrium, zirconium, magnesium, since those have an effect on the formation of domains and consequently on ferroelectricity. In summary, I just jump to the results. We found that differences in capacitance, DC drift, always correlate with the domain size, as it should be, according to the literature. As shown in the graphs on the right-hand side of the slide. So yeah, we have the delta C and we have the domain size. The analysis of the grain size and the chemical composition revealed that producer 2 uses additives like yttrium, while others control the domain size with a grain size of the ceramic powder material. On the top left graph, you see yttrium concentration, which leads to the formation of a thicker shell and thus a smaller core, and subsequently leads to a smaller domain size for producer 2. So all producer may not use the same techniques to control their ferroelectric behavior. Some do it by simply choosing the grain size, and some do it by choosing the right amount of additives. Up to this point, we have introduced the structure of MLCCs and barium titanate, and learned that capacitance is a function of voltage in those devices and that it relates to the domain size. However, capacitors in applications usually run for longer periods of time, like hours or days. So how does long time DC bias exposure affects the performance? Well, two processes can be distinguished, leading to an immediate as well as a long-term DC voltage dependence, as illustrated in the graphs here. Both processes are related to the ferroelectric properties of class 2 materials. The immediate effect is related to the dipole reorientation within the material domain structure, as illustrated on the schematic depiction here on the right-hand side. The immediate effect is in principle what we have just discussed. The long-term effect, also known as aging or second stage process, will lead to a further decrease of capacitance over hours or days. The degree of reduction is also dependent on the applied DC voltage. The larger the voltage, the less pronounced is the further relative decrease, as you can see in the plot here. At lower fields, the material is not in its final polarization state, hence we see a larger decline over time. At high fields, on the other side, you have a nearly full instant polarization, and thus you see only a smaller decline over time in those measurements here. There is a discussion going on in the literature about the exact origin of this long-term capacitance decrease. They are linked to the retarded movements of the domain walls. No matter what approach you find in the literature, they all somehow involve, well, domain walls. And they are also linked to domain wall pinning at defects. One explanation is the pinning is so speculated could then be released by charge neutralization of pinning sites by slowly migrating charges, as illustrated in the figure here. So at the beginning, the domain walls are pinned to the defects, and as charges actually are injected into the materials and slowly migrate through the material, those polarized defects may get disturbed or neutralized, and thus release, so to speak, the pinned domain walls. Looking at the relative capacitance change between the immediate and long time effect, one can see that there is clearly a voltage dependence. For intermediate or low voltage, the relative decline is about to 65% in this example and 75% at the rated voltage. But of course, no change at 0 volts because there is no field that could lead to polarization. And of course, there are also options to describe this behavior with a mathematical model. How could it be different? Which at this point I will only briefly mention for the sake of completeness. The equation given here, and any further discussions we may have after the talk, if you like. Well, in this depiction, 65% actually sounds like a lot, right? But you have to keep in mind that it is not compared to the capacitor's rated capacitance, but it's capacitance under DC bias, which is the immediate DC effect. Some producers may discuss these numbers, which kind of look significant, in such a representation or similar representation and compare their products in such a representation to other products and may draw some conclusion from it. And so you might think, no, oh, that's very complicated. Now I would have to consider two effects. And one of them is even so complicated, it depends on large time scales and voltage again. Well, it's probably not that complicated, as you will see. I would like to put the actual capacitance change of the two processes into perspective. So you may assess the actual practical relevance. For that, I have plotted the graph shown on the last slide in this 3D plot. The black point the black points are the measured immediate effect. The blue, green, and red graph is the aging effect for 50, 80, and 100% of the rated voltage respectively. The orange graph is the modeled long-term capacitance decrease. When looking at it, one cannot help but thinking, well, the long-term process does not too much, does it? And I think, yes, that's right. The long-term effect is certainly measurable and it may have an effect, but it is less significant than the immediate effect. Most class 2 MLCCs have production tolerances of 10 or 20%. Generally speaking, the long-term DC effect is about or even well below those tolerances anyway. So in some representations, you may find them normalized to those initial values, which then gives the impression of a significant capacitance decrease. However, as you can see right now, compared to the rated capacitance, this decrease is probably well within the production tolerances. So you may now decide if you think it's worthwhile considering it or not. Either way, the immediate effect is stronger than the aging effect. So it is important to remember that there are two effects, the immediate effect and the aging effect, while the latter is less significant. But what about the model to describe the polarization? Ferroelectric polarization, luckily, is well studied and models have been around for decades now. The figure on this slide shows the same measurement as before, as well as a fit with a well-established model by Miller. It depends on ideal assumptions such as complete polarization, homogeneous electric field, homogeneous dipole distribution, is based on homogeneous material composition, and so on. I will not go deep into the mathematical detail. only this much. The polarization is modeled with a hyperbolic tangent. The capacitance contribution, which is by definition the derivative of the polarization, is based on a hyperbolic secant. The model contains only physically meaningful and measurable parameters which were introduced before. The negative and positive going branch, denoted as P minus and P plus, are in principle the same. They are just shifted by EC by the along the x-axis. We model the total capacitance as a sum of the dipole polarization contribution to the capacitance and the pure capacitive contribution. Although the fit is not perfect, especially the features between -10 and +10 volt are well described by the model. When used on a measurement of a commercially available MLCC, the function does model the overall behavior. Certainly, however, if the voltage exceeds the 10 volts, the measured capacitance actually is larger than the calculated value by the model. Possible origins for this discrepancy could be that we are actually have multiple material fractions, as shall be discussed on the next slide. Here, as mentioned before, MLCCs do actually consist of a distribution of differently sized grains. It is not a homogeneous material. The multilayer electrode geometry is also not homogeneous. As indicated by the thin yellow lines, the electrode distance is not perfectly constant. Not only will we have a variation of the electric field strength due to the variation of the electrode distance, but also due to the electrode geometry. The multilayer electrodes consist of interdigitating layers, as mentioned before, which at the edges will have inhomogeneous electric fields, as shown here on the right-hand side of the slide. Hence, different material fractions are exposed to different electric field strength and thus will show a different effective voltage dependence. This is something we have to consider in the model as well. So what we have could be viewed as a superposition of different fractions that add up to the total capacitance. One could be now worried that this would be a rather messy fit. There are certainly many of these fractions. And how could that possibly help? Well, we could boil it down actually to three fractions. It turns out that one can find a model that is flexible enough, consisting only of a main fraction and two secondary fractions, as illustrated in the figure here. So I don't want to discuss the mathematical model in more detail at this point. It is worth mentioning that most parameters are related to physical properties and can be measured. This opens up the opportunity to model further dependencies, for instance, long-term DC effects or thermal behavior. For more information, please check out our application notes. Details about that are found in the references. So far, we have learned a lot about MLCCs and their polarization, and we even know how the model affect the polarization. Or if you even know how to model the effect of polarization. Yeah. However, some might ask, how is the model supposed to help? Well, since it looks somewhat complicated and I don't even have given too much detail up to now, the short answer is you don't have to do the calculation. we implemented it in LTspice. So what we did together with the colleagues from the technical marketing is the following. The measured capacitance voltage graphs, which are also freely available at the online database RedExpert, are taken and fitted with a model. With the fitting parameters, it is then possible to directly obtain the corresponding polarization or charge equation. So this step is required since LTspice needs the charge equation, which is the polarization. The model actually was designed from the very beginning that its charge equation uses only trigonometric functions available in LTspice. We do not have the time to speak more about this technicality, but the fact that the analytical integral of the capacitive model only contains simple trigonometric functions is an important feature of the model, actually. That practically allows an easy implementation in the simulation software. At the end, the user can download an LTspice file and use it in its simulation to find the best solution for its application. You then see directly what the capacitance decrease is without having to do the calculation, actually. Okay, wait. Not so fast, you could say. So far, we have only talked about capacitance. But what about the equivalent series resistance? All capacitors have losses represented by the ESR. Is it not changing as well? To cut a long story short, the ESR has only a relatively weak dependence on the applied voltage. What you see here is the measurement result for large AC and DC voltages taken with an impedance analyzer and measured with a boost converter that allows the application of high AC amplitudes. As you can see on the left graph, we measured ESR as a function of DC voltage. The dependence is, well, I would call it very low. Or considering the difficulties of measuring the ESR, one could argue that there is no change. It is instead an effect of the capacitive reactance. I mean, either way, we have a change of about 10%. I would consider it not too much. As you can see on the right graph, even for large AC voltage amplitudes of over 10 volts, we do not measure a significant increase of ESR as far as the measurement accuracy allows that to say. So the voltage drift for the ESR can be considered small, and the ESR is, with that, in good approximation, a constant. Whoop. Something went wrong. Okay. The LTspice model is based on the typical RC model then, which also takes voltage-dependent capacitance into account. This approach does, at the end, not only model the voltage dependence, but it describes the frequency dependence as well, as is shown here in the capacitance and impedance spectra. The dashed lines are the measured data from different voltages. It is actually the same set of data I have shown to you at the beginning of the talk. And the straight graphs are the predictions of the model of the RCL model with the voltage-dependent capacitance, with the model which I have just introduced to you. As you can see, apart from some smaller measurement artifacts, the model describes the actual measured data pretty well. So we can say we have a model that fits the real world at the end. Which brings me to the end of my talk, in which I have given you the introduction of ferroelectricity and class 2 MLCCs in general. I have roughly sketched the development of the mathematical model, which is suitable to describe voltage and frequency dependence of the MLCCs. So I hope I could illustrate the background and all the work that was necessary to create the LTspice model for our products. Also have a look at the Red Expert, where you can find a great deal of measurement. And well, I thank you for your time and your trust, and I hand back to Silas. Thank you very much.
Yeah, thank you, René, for the interesting presentation. Now we will come to your questions. Before we start with the Q&A, I will share the handout from the presentation today. So now you can download it on the right side. Okay, then I would say we can start with the questions. First question. You mentioned as so-called memory effect. What again was that and how is that important?
I may try to change or share my screen again for that. All right, maybe that slide. Oh, no, I started from the beginning. I don't want to start from the beginning. Okay, I hope everyone can see the slide. Silas?
No, we see the presentation
Mode? Okay, all
presenter
right.
view.
Yeah, I mean, the software changes changes the presenter mode, and I don't know how to fix that. So I will stay within the PowerPoint application. I have enlarged now the slide. I hope everyone can see it.
Yeah.
Why is that important? I mean, it is not important as long as you drive your capacitor always with a certain DC voltage and operate it under DC voltage. Every time you switch it on, you know that you will have a certain DC voltage, and then you can refer to the model, or you can refer to the measured plots in the Red Expert, read off the actual capacitance, and you actually don't have to care if there's this polarization state that is maintained even after you switch off the device. But sometimes people are interested to know if they change the polarity and if they change the value, then it actually might be important to know why we would see a lower capacitance value right from the beginning, for instance, because the material has maintained its polarization. The capacitance curve may have shifted, and what you see then, even at zero or low voltages, depending on which graph you are, you see a different capacitance. So in that sense, it could be important. I mean, if you operate your device nearly at full range or half, I mean, you should never design in at the full rated voltage. But if you are just interested on the effect at an applied voltage, you don't need to care about the memory effect so much. All you need to know is I see a decline and this is it. But you have to remember, some may have to remember, depending on the application, that once you remove the voltage, the polarization state is maintained, and that indeed influences the capacitance, may decrease the capacitance. I hope that answers the question.
Okay, thank you. Then I would say next question. Next question. How long will the material memorize its polarization state?
Very long. Basically, it can take hours, days, weeks even. As long as it is not heated above the Curie temperature, which is about 120, 130 degrees Celsius, it will remain the state of polarization. There is a certain decline even at room temperature for sure, but it is a very slow process. So it certainly is a long-term process. It is not characterized like on a regular basis for all part numbers, because as you can imagine, that would be very time consuming and would consume a lot of resources. Maybe just another interesting fact to know is, I mean, people try to build non-volatile memory devices based on an insulator made of barium titanate. So they build metal insulator semiconductor structures that can be utilized as a memory device. And as you can now maybe get an impression of that, I mean, this wouldn't be done if it would not be a long-term effect, if it would be lost after hours or so. So I cannot be more precise than that. It is a long-term process. The depolarization, the complete depolarization may take many weeks. I mean, after a time, you see, if you do the measurement, you see a slow increase of capacitance over the hours and over days, but it's a very slow process. I hope that answers the question.
Okay, thank you. Then next question. What are the effects of temperature on the capacitance values?
Well, I mean, as I said, the polarization will be destroyed as you increase the temperature above the Curie temperature. And I don't know if we have some plots at the Red Expert for different temperatures. I would have to check that, and maybe I can come back with a more detailed answer afterwards and send you an email about that.
Okay, thank you. Then next question. What can one do about the capacitance dependence of MLCCs during the design-in?
Well, all you can do is oversize. That's the basic strategy. That's what you do. You oversize the capacitance. That's what you always do. There's nothing else you can do. So you know at what DC voltage or voltage level you want to operate. You look up the DC the DC effect, so the capacitance decrease, and you oversize accordingly. And this is it. It's always the same, no matter what. There's nothing else you can really do. I mean, very often you are not able to reduce the voltage level of your application. What you also could do is maybe do some sort of oversizing, not only capacitance wise, but voltage wise, that you choose a capacitor with a somewhat higher rated voltage, and then usually the relative capacitance decline will then also be smaller. But then again, keyword here is oversizing.
Okay, thank you. Then I would say one last question. What is the voltage rating on the capacitor on page 4?
Should be 50 volts. So we measured up to 40, and I think the rated voltage for this one was 50 volts, if I'm not mistaken. I'm using throughout the entire presentation, basically just 2 devices, and the 10 microfarad was 50 volts. So we almost have complete polarization here.
Okay, perfect. Then thank you very much, René, for your interesting presentation and for all the answers. Yeah, thank you very much for listening. I hope you enjoyed it, and hopefully see us or hear us on our next webinar. And wish you a good day. And thank you, and bye-bye.
All right. Thank you.